Well, hi, and thank you for waiting and not going to the opposing track. So this work was done, this is joint work with Shlomi. OK, so Intel processor trace, or tracing in general. So a natural thing you'd want to do is know what executed and when. And you'd use that for debugging. It's used many times for reverse engineering and also for optimization. So let's say you've written some complex piece of software and you'd like to know why it's running slowly. Tracing is a natural solution. And most of the time today, it's done either by sampling. So that would mean firing off many interrupts and then just looking at where code is currently. Or another solution would be using instrumentation, which means changing the code and, say, adding timestamp checks. So recently, Intel introduced processor trace, which is a feature that enables you to know exactly what the processor is doing. And it has very low overhead. So the documentation says about 5%. And while processors did have such a feature, it used to incur slowdowns by tens of times. So I think the documentation was about times 30 or times 40. But now you can trace, and you can be on YouTube, and the movie will just run. So it's been available since Broadwell, so Broadwell, Skylake, Kaby Lake probably. And a similar feature called real-time instruction trace exists on certain Intel Atom processors. So that's a different line of processors. So what information does the processor actually need to give you for you to know exactly what run? So it telling you exactly which instruction just run would be a little excessive. So it'll give you less information, but just enough. So if you look at the top black arrow, and so you need to know whether that if was taken or not. So that would be 1 bit, right? But if you look at the bottom arrow, where you have an indirect call, you actually need the instruction pointer. And that's what the processor will give you, no more. Once you turn on this tracing, the processor will write out the trace to memory. And while there are quite a few packets available, the ones that we'll mostly be interested in are taken, not taken packets, instruction pointer packets, and timestamp packets. And the important thing to remember, and we'll go over this a couple of times, is that you do need the binary to decipher what just run. So returning to the code from the previous slides, on the right, you'll find how those packets look like when they're decoded. So usually those taken, not taken bytes, which correspond to that if, they'll usually be packed together. And you can see the instruction pointer in full for the indirect call. So even if you are tracing, you probably wouldn't want to trace everything at any given point. So you can configure to trace user land, kernel land, or both. You can filter by processor. And you can filter by address range, either starting to trace in a certain address range or stopping, which means, let's say, only a certain module interests you, so you could just trace that. Another thing you'd be interested in is tracing virtual machines. Well, the Intel Atom processors that support tracing, they support tracing the guest and not the hypervisor. Broadwell has no such support. And on Skylake, you can trace the hypervisor or the guest or both. And as I said, you're going to need the program's binary to decipher what just run. See, because you only have like 1 bit for, say, conditional branches, or nothing for calls that are relative to the current instruction pointer and so forth. So what if you want to use processor trace right now? Well, Linux kernel 4.1 already has a support. So that means the kernel code to turn on those processor features which are privileged. In kernel 4.3, it's already integrated with the user tool perf. So you could just run it easily from a command line. Also, if you just want to decode the packets, Intel has an open source library for that called libipt. GDB 7.10 enables you to trace using processor trace, just as it does with branch trace store. And there is an open source driver called SimplePT, which I used for the previous slides, which will enable you to use processor trace even if your current Linux kernel is lower than the ones that I mentioned, say 4.1. OK, so as I said, this is going to be an anti-exploitation talk. So this is your high shellcode PDF. And due to the NX bit, when the attackers want to run their shellcode, it will usually be allocated in memory that isn't executable. So what they do is use code that is currently executable. And one of the prevalent methods is return-oriented programming, although it really does come in many forms. So in return-oriented programming, what you'd see is that the code suddenly starts moving around rather strangely. Functions might not return to their callers. Or during the exploitation process, you'd see calls to the middle of functions, which make no sense. So control flow integrity is a set of rules that impose certain rules which impose how the code flows. So basic rules would be functions return to their callers, you don't call to the middle of functions, and so forth. But how would you enforce those rules for anti-exploitation? So one thing you could do is just add the checking code in the binary. So those of you who have heard of control flow guard, which is now in Visual Studio from the 2015 version and late updates to Windows 8.1 and Windows 10, you'd compile the check. The checking code gets compiled into the binary, and there's support in the operating system. And both of those work for forward edges. So certain indirect calls will be checked to see that they make sense, that let's say they call to the correct functions. Another way you could enforce those rules is just trace the process and then just go over it and see that it's OK. And that's this line of work. And another line of work is to use other CPU features from the performance monitoring unit to detect surprising branches. So when you see a return that the processor doesn't expect, well, that's surprising. And the processor will let you get an interrupt for that. And then you could check. And then you could see that the return didn't match. So if looking at prior work, so the K-bouncer work in the second bulletin is similar to this work, or vice versa, I guess. What it does is it looks at, so K is kernel bouncer as like the people not letting you into clubs. At certain syscalls, it would check the last up to 4 or 8 or 16 branches. It uses a feature called last branch record. But basically, it looks at the previous branches in some sense like tracing, but a very, very, very small part, which is similar to ours. And most of the other work uses the performance monitoring unit that I mentioned. So as I said, we do anti-exploitation with control flow integrity. And our implementation, it detects illegal returns, but we could just as easily do forward edges or moving around between modules, because there are usually certain ways in which functions are imported. So you could look at that as well. And it was developed in 2015, and it's soon to be open source. So how would you verify? How would you verify control flow integrity using processor trace? So basically, if you're looking at the binary on the left, you just move around your finger and just make sure that you don't call to the middle of the functions or return to where you weren't supposed to return and so forth. So it's fairly simple. But what would you need to do that verification? So you would need the control flow graph. So that would be a graph with nodes consisting of basic blocks, or you could think of basic blocks and functions. And you need to know where those are, right? Because let's say you suddenly see an instruction pointer. You need to know. Let's say you see an indirect call. You need to know that that calls the beginning of a function, but you need to know that there is a function there. So you need that control flow graph. And if the example I want you to keep in mind is checking whether a certain PDF file currently opened by Adobe Reader is trying to exploit you, is exploiting a vulnerability. So the modules that you need the control flow graph for in order to go over the trace are Adobe modules and Windows modules. And you don't know where the functions and basic blocks are for those. For Windows, you might have public symbols, but for Adobe, you wouldn't even have that. So you need that control flow graph to go over it. So a standard method is using static analysis, which is what we did. And we used IDA for it, but you could just as well use any other thing, Binary Ninja in one of the previous talks, or Anger. But IDA didn't do a good enough job because there are functions and basic blocks that it didn't recognize. So if you'd be tracing that with your finger, you suddenly get to data, and you wouldn't be sure whether that was legal or not. So what we did, we took the control flow graph from static analysis, and we also did dynamic analysis, just running many benign PDF files and going over the trace. And when we had to update our control flow graph with CFG, we just did that. Okay, and then in the end, we had our CFG for, say, a certain version of Adobe Reader on a certain version of Windows. Now, it's important. So a very naive and rather foolish way of implementing this would be to really go over every instruction that gets executed, and when you see a branching instruction, moving your finger. But that would make no sense, since you're only interested in branches. Move ESI, that makes no difference to you. So it makes a lot of sense of just saving the control flow graph and going over that, because if you're looking at a PDF file just opened by Adobe Reader, many instructions get executed, and you do want to go over that trace rather quickly. So it's important, but also rather obvious. So what information do you need? I said that you can filter by process, but when you're going over the trace with your finger, you're actually going over one single thread. But there might be many threads of Adobe Reader running on exactly the same processor, right? So if you remember the trace packets on the right in previous slides, you'd actually want to highlight which line corresponds to which thread, so you could trace it with your finger, right? So you need that thread information, but the processor doesn't know about threads, right? It only knows about processes. So how would you get thread information? Well, on Windows, what you could do is use event tracing for Windows. It's rather cumbersome at times, but one of the events that exist there are context switch events. And you could use the timing given there together with the timing that I mentioned from processor trace, and then just sync those. And then you'd know, OK, now this thread started running, so you'd highlight the lines below. And then you'd know, OK, so my yellow markering is thread number 1, and so forth. But for some reason, that didn't really work for us, but we were using a Broadwell processor, and timing has become more accurate on Skylake, and we probably could have got it to work anyway. So a different solution would be to try to get a callback each time a thread gets context switched in, right? So if you're currently recording the trace, and you now see, OK, I've been called, so I'll just mark, OK, thread number 1 started executing, and then you know which part of your processor trace, which part of the trace corresponds to thread number 1. But as far as we know, there's no direct way in Windows to get that callback. So what we did, and some of you might have cringed already, was we hooked the Windows context switch function, which we wouldn't do we wouldn't do for a product. But in their Black Hat lecture, Endgame presented a way of doing this using asynchronous procedure calls. So it's a kernel mechanism to get a callback when a thread gets switched in. And it's fairly straightforward to get what you really want from that. So that'd be a solution. But as I said, you always need the binary to get back the instruction trace, right? So you need to know which pages of the process, when you're going over the trace, which ones are currently executable, right? Because you need to know whether calling them is legal or not. So you do need the module load unload information. Well, getting that from the event trace for Windows is rather trivial, and we just synced those. What you do need to remember is that with processor trace, you only get where the code currently is. So you won't get the string of the module that's currently being loaded. But you do get that from event tracing for Windows, so it is rather trivial. Well, we're still not exactly done, because there are cases where not returning to your caller is legitimate, right? So one case you could think of is when an exception occurs, right? Let's say you have a try and except, and you might return to a function way up the call stack, right? And that would be legitimate. In the windowing system, you could see user mode callbacks. So you'd see a syscall to, say, win32k. And then when you'd return, you wouldn't return to the instruction right after, but to some other place. So you need to deal with those, because those are legitimate. And if you'd flag them, they would be false positives. So how we dealt with those is with binary signatures. And it would be rather daunting if we'd had to do that for every application version that we want to support on every operating system. But it turns out that this is more of an operating system issue than an application issue. So you wouldn't have to do this for every version of Adobe Reader and Word and PowerPoint and so forth. How about dynamically generated code? Well, it's almost entirely not dealt with by our implementation, which means JITted code. One of the reasons is that you need the binary at every point. So let's say a page is writable and executable at the same time. In order to trace it, you'd have to know what got written at every point. So one of the ways that you could do that, which we didn't, is to remove the write permission and then just deal with the access fault every time it gets written to have the current version of that page while you're tracing. But we didn't do that. A case that OK, I'll just get to that a bit later. So how about our results? Well, we ran the system on a couple of thousand PDF files, doc files, PPT on benign files, and there were no false positives and on a handful of malicious files. And we did detect the control flow violations, and really not flagging the benign files is the trickier part, right? Because there are quite a few cases where not returning to a caller, say, is legitimate. So let's forget about CFI and anti-exploitation for a second. And what if you just want to use processor trace for what it was intended for, probably, which is tracing, right? Just using very fast tracing. So what would you need? You'd still need the module load unload information because you need to know what's currently executable, and you'd need the thread context switch times, which I mentioned. But you could probably do without the control flow graph, right? Because you're not trying to enforce a CFI. Coming soon to a motherboard near you, in June, Intel announced control flow enforcement technology, which deals with two of the problems that I mentioned. So if you've been paying attention, what we're actually doing is we're saving shadow call stack, or at least for the returns. And it would be nice if the processor would just do that for you. And then if it would see a return that it doesn't expect, right? Because when you call a function, right, you know that it's supposed to return just to the instruction right after, right? So the processor essentially knows when those returns don't match. So in some time in the future, and they didn't say when, processors will support getting an interrupt once that return doesn't match. So you wouldn't have to do all the tracing that I just mentioned. As for forward edges, so yeah, let's say you'd want to know whether an indirect call is legitimate. So what they do in control flow guard is that every byte of the process memory, it's represented with a bit which says whether a function starts there or not. And that gives the attacker a number of bits that he could call, and the enforcer, the one doing the verifying, he wouldn't know exactly where the function started. So how Intel is dealing with that is there's going to be a new instruction, and you could ask the processor to interrupt you. You can ask the processor to interrupt if a call is made and the target doesn't start with a specific instruction. So that's more accurate, okay? Instead of instead of letting the attacker move around. But as I said, they didn't disclose as yet when which processor line is going to support this. So how about tracing quickly on ARM, right? So there's a very similar feature to processor trace on ARM. It's called CoreSight. The integration with perf has already been done by Linaro, or at least part of it by Linaro. Again, you need some sort of library to decode the packets, and there is such one that's open source named OpenOCD, OpenCSD, and you could just go to that link to find out. So how about bypassing CFI? So one thing you could do, right? So if you're trying to exploit a vulnerability and you can call a function and control its arguments, one would think that that would be enough in some cases, and it is. And that's exactly what's used in control jiu-jitsu. It turns out that the control flow graph usually will enable you to rather easily call functions and will rather easily have a path to functions that are dangerous, say like exec or system and so forth. And if you control the arguments to a function that calls a function that calls exec or system, and many times that would be enough to circumvent it. And the important part is you're not violating control flow integrity because you're just using the regular control flow graph. But how about a more data-oriented attack? So this was mentioned in write once, own anywhere. Some applications have a variable that basically gives you the privilege level. So if you could just change it, right, you'd suddenly go to God mode, say. And obviously, since this is a memory attack, again, you won't be violating the control flow. This is another one that I liked. It's called control flow bending, and this is a data attack again. And what they show is, let's say you have a call to a function like, printf or similar functions. Then if you control the format string, let's say you can use your vulnerability to control the first argument to that function, well, you can get arbitrary computation. And if you got there without violating control flow, then you've just bypassed it, right? Because you got arbitrary computation. And the last one is in some sense similar in spirit to return-oriented programming in the sense that it has gadgets. So think of instructions in a sort of virtual machine currently controlled by the attacker. But the gadgets, but as I said, return-oriented programming usually violates control flow integrity. What those gadgets do is usually a structure of load from memory, do an operation, and then store the result of that operation back to memory. And then you'd want to, and that would be, you could think of that as a basic operation in your sort of attacker virtual machine. And you'd want to chain those in order to get your arbitrary computation. And you wouldn't think that to be that trivial. But what they did is that they looked at the binary in an intermediate representation, and they used the loops there to move from one gadget to the next. So that would be, if you're thinking of return-oriented programming, that would be what the stack and return do, right? Because they let you move from one gadget to the next. And they use the vulnerability to choose which gadget they'd want to use currently. And in that way, they get arbitrary computation. And they had relatively good results. It wasn't completely automated, but it did work on a couple of applications. I thought it was very interesting.